All right, welcome to the 11.1 practice homework review. This was the one where we had to set up our own equation using either story problem or the zeros, and then actually try to figure out the standard form, so distributing. So this might be kind of a long video because of the distributing that we have to do for 14 through 17, but let's start looking at number 11. So this is one of those weird situations where we have a box. I promise you this won't be on the quiz, but we do need to realize how this math relates to the real world. So the Acme Box Company has an order for rectangular boxes from the Speedy Delivery Company. Speedy Delivery Company's policy has limits on the size that the box can be. They use a rectangular pieces of cardboard that are 24 by 36 inches. To make these boxes. The boxes are made by cutting a section out of each corner that is X by X. These boxes are made, okay, so what that means is those corners are cut out and it's kind of left us with this weird shape that then folds into a box. So if I draw the 3D shape, all right, the height of the box we got from the little corners that we cut out. So that will be X. And then the rest of it is that little gap in between. So I'm going to change my color so you can see this a little bit easier. This piece right here and right here is right here in the folded box. So that was 24. This whole thing was 24. We have these two x's that we took away. So that's 24 minus 2x. Likewise, we had the entire cardboard piece, which is 36, and then we took away these two x's. So it's 36 minus 2x would give us this chunk right here on both sides of the box. So it's 36 minus 2x. So when we find volume, and I'm going to move on to the next page for this. When we find volume, sorry, let me go landscape, didn't realize, nope, can't do it now, too late. So we need to write the volume. So the volume of the box, and this is number 11 then, volume of the box is the height times the width times the length, which would be x times 24 minus 2x times 36 minus 2x. So let's deal with the more complicated part. So let's FOIL this out. 24 distributed to the 36. That would be 864. 24 distributed to the negative 2x would be minus 48x. And then we switch what we're distributing. Now we have the negative 2x, distribute that to the 36. That's negative 72x. Distribute it to the other negative 4, that's positive 4x squared. I don't like my x's out of order, so let's rearrange it. So we have, bring this down, x times 4x squared. We can combine like terms. And then 864, and then now we have to distribute that x, which is a little bit easier than what we just did. All right, so this is volume in standard form, and up here was volume in factored form. So sometimes we want one, sometimes we want the other. Here, I told you I wanted standard form. If we look at number 12, it says use the equation you wrote in item 11 to determine the maximum volume of a box that we can deliver. So what we need to do here is we need to go to Desmos to graph it. So I'm going to, thank gosh I had it right there. graph this equation. So we said it was 4x to the power of 3 minus 120x squared plus 864x. Now, let me double check that. 4x cubed minus 120x squared plus 864. All right. If we look at our graph, it's kind of crazy, right? We don't see the hump. That's clearly because we don't see everything. So let's just try to play around with our y-axis. Let's just say, let's go huge. Still not huge enough. Let's add another 0, so 10,000. So we can kind of see it, but that's still kind of no good. So let me change it. Looks like it cuts off at 2,000. All right, that's a little bit better. Decimals, we're lucky enough where we can find the maximum by just clicking on it. Otherwise, we have to do it another way. So when we look at this, we have this equation for volume. And we know it has this maximum, relative maximum at x equals 4.7 and y equals 1825.3. So let's go back to our problem. It asked to find the maximum volume. So the max volume is the y value, because that's our equation, and we said it was 1,825.3. And we do know the units here should be inches because it's volume cubed. So that should be it. And then lastly, determine the possible domain for the construction of these boxes. So let's again look back at the graph. We want to figure out where does this graph give us a positive volume. Since we can't ever have a negative volume, we want it positive. So it looks here that it becomes positive starting at x equals 0. It goes up, comes back down, and crosses the x-axis at 12. If we look over here, we have this weird 18 thing going on, and then it becomes positive again. But that, if we look back at the drawing we made, we know that our box can't ever be bigger than 36 on this side, the vertical side, or can't be bigger than 24 on the horizontal side. So that's kind of where we got this from, right? We set this equal to 0, we get x equals 12. That will be the max of our domain. So our answer is our x's have to be between 0 and 12, ideally somewhere not on the other extreme of that. We can also represent it with our interval notation as 0, 12. So moving on to the next, this is now leaving the story problem of the boxes and just doing the work of finding our equation. So for 14, we say we want degree 3, and we want these zeros included, -2, 3, 7. What we always need to ask ourselves is, were we given all the zeros that we needed? So because it's degree 3, that means there's at max 3 x-intercepts, or zeros. If we look up here, we have all 3, so we're good. So now we need to write this into factored form. So this is the easy part. We will then have to distribute after that, which is not the easy part. So let's work on this. We have these 3 zeros. these are the zeros, which are not the same as factors. The difference is, remember, if we had like x minus 1, we would set that equal to 0 to get x equals 1. So this is the factor, this is the 0. So notice how the signs change. So we need to write this into factored form, and we need the signs to change. So the x squared, the 0 of -2 turns into x plus 2. The 0 of positive 3 turns into x minus 3, and likewise for x minus 7. So when we have to distribute this, we have to just take our time with it, use our arrows, so we get x squared minus 3x, and then we distribute the 2. So then with the 2, we get plus 2x minus 6. And then we can just bring down the next thing because we have not dealt with it yet. All right, so now we can combine like terms, which are just the middle two. So we have x squared minus x minus 6 multiplied by x minus 7. So we can just keep this process going. All right, we can distribute. I'm going to go this way now because it's a little bit less work for me. So x cubed minus x squared minus 6x. And then we distribute the 7 next. So to every term inside the other parentheses. So we get plus 7x squared. Oh, no, we don't, because that's minus 7. Minus 7x squared plus 7x plus 42. So now when we combine like terms now, we have x cubed by itself, but then we have these two terms that are both x squared. So we have -1 plus -7, so -8. And then we have -6x plus 7x, which is just positive 1. So you can either keep the 1 there or not. And then lastly, the 42 by itself. So again, we have factored form and standard form. Pay attention to what I'm asking you for on the quiz. It depends how I'm feeling and what I want to see from you, whether or not I ask for standard or factored. So let's move on to 15. 15 says we want degree 4. And these are the zeros that I give you. I give you -1, -1, 3, and 3. All right, so if we look at that, we have our zeros repeated. So that means there is multiplicity here. So if we graph this, we know it would just come up to the x-axis, won't cross it because our multiplicity is even, comes up and then comes back down possibly, or something like that. We're not too sure because we get to make up our equation. So factored form is easy because all we do is just change the sign. So x plus 1, and then x minus 3, and x minus 3. We could have rewritten this using the power on the outside to save us some time. But if we do that, then distributing is going to be more difficult. So I'm going to move this over here. Somehow it stole those parentheses. All right. So let's deal with it here. So we are going to kind of treat these as two separate foiling. So we have x times x, which is x squared, and then x times 1, which is just plus x. And then we'll do 1 times x, which is plus x again, 1 times 1 plus 1. That's the left. On the right, we're going to do x times x, so x squared, at x times -3, minus 3x, -3 times x, and -3x again, and then -3 times -3, which is positive 9. So we can clean up our like terms. All right, so now we have these. We still have to distribute them, but now we have a little bit more complicated because we have a lot of arrows to work with. So we have x squared times x squared to x fourth, x squared times negative 6x, which will be negative 6x cubed, x squared times 9 plus 9x squared. Then we move on to the next term in that first parenthesis, 2x times all three terms. So 2x times x squared is plus 2x cubed. 2x times negative 6x is minus 12x squared. 2x times 9 is plus 18x. And then our last one that we have to work with, so we have plus 1 times x squared, so just x squared, plus 1 times negative 6x, so it's just minus 6x, plus 1 times positive 9, so plus 9. So now we have to rewrite these all together to get our final standard form equation. So x to the fourth has no like terms, so it says x to the fourth. Negative 6x cubed has some like terms. It only has one other like term. So we have to add those two coefficients together to negative 4. Next one, x squared has a couple like terms, so we do positive 9 minus 12 plus 1, so that will give us minus 2. Then we have 18x and negative 6x, so that would be 12x. And then lastly, the plus 9 at the end. So that would be our standard form. Let me rewrite it away from the bottom and a little bit bigger. All right, that is our standard form equation. The next two is kind of getting to a little bit more spread out of a situation. These are going to be quite lengthy, so let's just start the setup and let's move on to the next one, because I want to talk about something that has a complex number in it, because that was something we kind of talked about a lot later on. So let's move on to 16. Here we have degree is 3, and our zeros that they gave us were negative 4, 4, and 15. So degree 3, we have all three zeros, so that checks off. So when we write our standard form, our factored form, we just change the sign. All right, so that's in factored form. Then we would have to distribute to get standard form. All right, we practiced that enough. I'm sure you can handle it now. So degree 5 is next. And then let's see how many zeros they gave us. They gave us negative 5, negative 3, 1, 0, and 4. So they gave us all 5, so that checks out. So let's write it in factored form. So we have to change the sign. All right, but now when we get to the 0, we have x plus 0. Notice the mistake that I made. We have x plus 0, which we don't really need to write because this means nothing. So we can rewrite this without the 0 there, or you could just skip that step entirely and just wrote that x by itself. But we don't really like that all randomly, so we usually put the x by itself out in front and the rest of the factors over here. So that would be the factored answer. Again, we can distribute it to get to our standard form. Next up, 18. We kind of have a scenario here. After finding a polynomial with real coefficients of a given degree with given zeros, how could you use a graphing calculator to check your answer? So basically it says, and we can use the answer above. So we have a given degree, we have our given zeros. All right, let's say after we distribute, we get this crazy equation. We don't know if we did our work correct. Probably not. I will assure you that if we actually did what we're about to talk about, this would be very, very wrong. But if we look at this, how could we check that our answer was correct? So what we could do, step 1, graph our function. Step 2, check to see if the x-intercepts of the function are the zeros we were given. If we had different zeros, that means we made a multiplication mistake. If we have more x-intercepts, that means we somehow made a mistake on our degrees. We could spot any mistake we made, because if we made any mistake, big or small, if our graph has different x-intercepts than our zeros, something happened. All right, so that's how we can check. 19, last question. The number of zeros will be even. Reading the answer. The polynomial function only has complex zeros. So remember, our complex zeros might look like this. 3 minus 2i, right? And I usually only give you the positive one, and then you have to know, all right, assumed that you know the conjugate is also a root. Which means it is also 3 plus 2i, and all you change is that middle sign. So complex zeros always have to come in pairs. So if we only have complex zeros, we will have only pairs of complex zeros, which means the number of zeros will be even. So we can write that complex zeros only come in pairs. So we can only have an even number of complex zeros. All right, so that's it for this homework. I will be posting all 3 homeworks on the same day, so good luck.